The last time we started covering clustering. Clustering is an unsupervised learning exercise. It's a part of pattern recognition. This is quite different from predictive modeling. In predictive modeling, we are essentially trying to generalize the relationship between input and output as some underlying function, fx, such that we can use that function, that generalization or that function as a relationship to make predictions in the future. Now, the target variable can be numerical, in which case it's regression. It can be categorical, in which case it is classification. Cats and dogs, classification, and the amount of ice cream you would say is regression. More prosaically, what would be the home value of your home based on certain parameters is regression, isn't it? Whether or not, given a test, you have COVID is a classification problem based on, let's say, some X-ray parameters and so forth. On the other hand, pattern recognition is not making any prediction. It's just saying there are hidden patterns in the data, and those patterns are worth discovering. They need not even be hidden. But for a machine, it's a little bit hard to find out. As I mentioned, the human eye has gone through at least 100 million years of evolution. So for us, we immediately see patterns as human beings, and probably most mammals, most animals see patterns, clusters immediately. It's a wonderfully intelligent machine, the human eye, or the eyes of animals. But machines, of course, don't have eyes. They have to discover patterns mathematically. They have to learn the presence of patterns. So that is the field of pattern recognition. In pattern recognition, we talked about quite a few things: clustering, dimensionality reduction, anomalies, and outlier detection. These are all exercises of pattern recognition. They look at certain aspects of the data or certain pattern in the data. We focused, and we are still focusing today so far, on clustering. Clustering is the exercise in which we look for clusters in the data. I mentioned that clustering is not an exact science, because how many clusters you see depends on the granularity or the resolution at which you are seeing. And sometimes it can be ambiguous how many clusters there are in the data, especially if the clusters are not very well defined. And then there are clusters within clusters, you have subclusters and so forth. So all of that makes for the very interesting subject of cluster detection or clustering. Now, how do we do clustering? We do k-means clustering. K-means is the exercise in which you say, I don't know how many clusters there are. Tell us how many there are. Well, that is the value of k. If you tell us what k is, then it's a simple exercise to find the clusters. Its primary purpose is to just pick k initial points. Now, you can randomly pick those initial points, or you can use a little bit more intelligent heuristics. So, for example, one heuristic could be, if you're doing a two-means clustering, you take a point, random point, and then you take another point as far away from it as possible, right? So that would be the choice of initial points. Then what do you do? After you have the initial points, declare them to be the center of the clusters, or the center of gravity, or the centroid of the clusters. One intuition that I ask you to have is, think of each data point in the feature space as sort of a mass point in real space. So then you would see areas that are, wherever the clusters are, every cluster will have a center of gravity, like a centroid. And these initially, what you do is you find the centroids, then the remaining task is to take every point and ask which centroid it belongs to, which is equivalent to saying which cluster it belongs to, because the identity of the cluster is the centroid. So once you have done that, now you realize that initially you started with a guess. Now what you do, you need to have a cycle, a loop that repeats. The loop is, once you have found or once you have partitioned all the data points into clusters, now for the clusters, recompute the centroid, the true center of gravity, You do that. And once you do that, once again, reassign all the points to the nearest centroid. And you keep repeating this cycle till you notice that either the centroids are not moving or points are not changing loyalties from cluster to cluster. And there are many variants of k-means clustering that use one or the other. You can keep doing that. So that is the algorithm of k-means clustering. There are many adaptations to it. For example, uh, instead of k-means, you can take the median, right? Instead of the average, the middle guy, and so forth. Or so that would be the medoid clusters. You can, instead of mean, you take the median. We all know what medians are. Or sometimes the big problem is that you have a million points and assigning 1 point at a time to each cluster can be rather slow. You can expedite it using entire regions of the feature space and associating it with a centroid. Those are ways to accelerate k-means clustering. There's a vast body of literature, starting with the oldest method, KD trees, a data structure called KD trees. Um, and then over time, people have adapted and created a lot of these structures of partitioning the feature space into regions, and those are called metric spaces. Um, and what they do is they make k-means clustering pretty fast, especially when we live in the world of big data sets. Now,
Asif,
yeah.
is the distance different, like when I use k-mean versus the k-median?
No, you still use the Euclidean distance generally, and that is a very interesting point you raise. What is the notion of distance between 2 points? As far as k-means is concerned, it is silent on the question of distance. All it says is that so long as it agrees with the basic notions of distance, whether you use Euclidean, Manhattan, whatever it is, it doesn't matter. Right? Any notion of distance. Now, just to whet your recollection, what is the notion of distance? I think that may be worth reviewing. So let me review that. Technically or mathematically, in any feature space, any Rn space, if you define a function that follows these three criteria, that follows the following criteria or condition, that follows the conditions. One is that function d of a point to itself, the distance of a point to itself is 0. In other words, if two points, or let me mark it as y, if 2 points in this feature space, if the distance is 0, if and only if x is the same as y. In other words, those 2 points are co-located. They are the same point in the feature space. The other thing is that distances are always a positive definite, greater than 0. And obviously, this condition comes with the fact that when they are the same, it is 0. Uh, 0. And also, this is the symmetric. This is built into it. The distances are symmetric. The distance from your living room to the kitchen is the same as the distance from the kitchen to the living room. That sort of thing. Now, and the other distance is that it is called the Schwarz inequality, which says that suppose you have a point x and y in the feature space, then if you take any arbitrary point, other point z, then distance between x and y will always be less than equal to the distance from x to an arbitrary point z plus the distance of z to y, right? So this path will be longer than this path, the shortest path between these 2 points. So this is the shortest path. Shortest path. The shortest path, there is a name for the shortest path. It is also called, shortest paths are called geodesics. It's a term that you'll see me here speak of. People who are mathematically inclined, and especially machine learning textbooks tend to be, and papers tend to be, you will often be surprised by the word geodesic. The geodesic simply means the shortest path. And generally, geodesics imply that your space may not be very linear. It may have curvature and things like that. Otherwise, you would just use the word straight line. Like, what's the difference between a geodesic and a straight line? If you look on the surface of the Earth is like an apple shaped, right? So the shortest distance between 2 points is a curve. It's an arc. It is not a straight line. So the shortest distance of the geodesic is not necessarily a straight line. Something to remember. Of course, if you could go through the Earth, then you could do a straight line. But if you are bound to the surface of the Earth, the way an aeroplane flies or a ship sails, then you have to go along the geodesic. That's the meaning of the geodesic. So that's the notion of a distance. Are we together, guys? The most common distance that you can think of are Euclidean distances, of course. What is the Euclidean distance between x and y? It is equal to the square root of, what is it? X1 minus y1 square plus x2 minus y2 square plus go on. Plus, suppose you are dealing with n-dimensional space or three-dimensional, whatever it is, xn minus yn square. Do we all agree? Like in 2 dimensions, it would be just x. Oh, sorry, I use x1. There's no reason for. Yeah, so x1 component, x2 component. Are we together, guys? Huh? Assuming that the axes are x1, like x2, x3, right? Does this look obvious, guys? Can I have some feedback?
Yes.
This is obvious, right? And if you remember, I talked about the Manhattan distance. Manhattan distance was, this is often called the D2 distance, the D1 distance between x and y is equal to, what is it? X1 minus y1 plus x2 minus y2 plus xn minus yn, absolute value, right? So this is the Manhattan distance. And if you remember, long ago, I taught that the generalization of this to Minkowski distances. The nth norm is a very simple generalization of this between x and y. X and y are, let's say, 2 points distance in Rn. This is sorry, in Rn is defined as, or what is it defined as? It is defined as x, the component xi minus yi, absolute to the power n, and the entire thing obviously summed over I, and the entire thing to the power 1n. Right? So here it is, for Euclidean is the square root. Square root is the power half. And this is called a generalization of the notion of Euclidean distance. So you can play with many distance norms, though from what I know, most of the time you go with just Euclidean distance, occasionally Manhattan distance. Right? These are the distances that you typically deal with. But the notion of distance in machine learning or in mathematics is much broader. Anything that follows the Schwarz inequality is a proper definition of distance. So anything that, not just the Schwarz conditions, are these things. These are the definitions of depth of distance. Are we together? And this is the way you should remember it, guys. That we are taught in high school only Euclidean distance, but generalize beyond that. It's a very straightforward generalization. A distance is any function in feature space, scalar function, that follows these rules can be considered a distance function. So on a feature space, you can define all sorts of distance functions. And in particular, the Minkowski norms, many norms are defined in feature space.
Yeah, Asif, can you also clarify between difference between norm and metric? You mentioned metric some time back. So what's the
Okay,
difference
just a
between
distance.
those?
Another word for a distance is metric. A distance, the function d is
Okay.
called the metric. That itself is a metric. The reason this word gets a little bit tricky is that, see, a lot of this literature is borrowed from theoretical physics. So what happens is when the space is curved, right, or when there's a curvature in space, let's say on the surface of a sphere or things like that. So then people often use the distance between 2 points, right, is often given um, as d mu mu, right, dx mu dx mu. So in other words, if you take two small points which are like in which the distances are very small distances between this is the delta d, a small distance between 2 points. Let me just call it the first and the second point, and there's delta x, right? So what you do is, or dx, you can think of it as, well, I use the word d here, which is unfortunate because d also stands for derivative, but let me just call this delta distance. So here, this quantity is called the metric tensor. It's a little bit of a mathematical thing. I'm giving it to you in all its mathematical glory, I suppose. This is your mathematical tensor. What it means is that it is not so straightforward. Certain distances are stretched out like a rubber band. Maybe someday I'll go a little bit more into explanation of it. So
Okay.
people often distinguish between a definition of the distance, right, and the metric itself. But for very small distances, uh, this quantity follows the Schwarz inequality, and so this entire thing is called the metric. So people use the word metric in machine learning a little bit more loosely than the way they would use it in theoretical physics or for example, theory of relativity, space-time physics.
Asif, I have a quick clarification. Uh, the Manhattan is norm n equal to 1, the Euclidean is n equal to 2. These two is kind of in the physical world we are able to imagine. When you draw a line between 2 points, that tends to be n equal to 2. But what would be n equal to 3? I just wanted to get a little idea because I can't even think about it.
Okay, so let me give you an intuition. See, um, Euclidean distances as the bird flies between 2 points, straight flight, right? The Manhattan distance, the word comes from Manhattan because Manhattan is laid out on a grid, right? So the city of Manhattan is like this, right? So suppose you have to go from here to here. Euclidean distance would be this, but that's not how that would be as the bird flies. But a taxi cannot go like this. A taxi is supposed to go like this. An Uber or a taxi would go like this, or it would go, it has many paths associated with it. It can go like this, or it can go like, this, or any one of these paths it can take, intermediate paths it can take. But whatever path you take, it will be at this distance plus this distance, absolute term. So the taxi driver's distance is the Manhattan distance, or the first norm. As the bird flies is the second norm. The third norm is actually a little bit harder to distinguish, or a little bit harder to tell, because it tends to be, how should I put it? It's a bulbous. If you look at the center and you look at all points that are Manhattan distance, one unit distance apart. Circle is like this. This is Manhattan. A circle in Manhattan distance would actually, to our eyes, look like a diamond shape. And in Euclidean distance, of course, it looks like the familiar circle. But in higher distance, it takes to be more bulbous. It begins to look like this. as you increase the norm, it begins to develop this extra curvature. Now, in this, it looks weird, but what it means is that it sort of shrinks the space between 2 points. The absolute value of distance will be much, much less. Are we together? And
Asif, I see the distance with the bulb green, it's much larger, right? The distance between those 2 points.
yeah, it is counterintuitive. What you're saying is that if even if far away points are actually at unit distance in the fourth or fifth measure, then what it means is that somehow the far off points have been pulled in. See, think about this. If you're going by the red path, it is a pretty long path. When you go by the green path, in a way, this distance has been pulled into a shorter distance, isn't it? In absolute terms, the value is shorter. So when you go to the third norm, fourth norm, or the infinity norm, the distances keep shrinking. The absolute value of the distance keeps shrinking. Right? It's almost like you find some magic way to tunnel from one point to the other. Just as for a taxi driver cannot, but you can imagine to the taxi driver, the bird has somehow tunneled through the grid.
Mm-hmm. Oh, got it. Okay, I got the. Yeah, I cannot imagine, but I got the intuition.
Yes.
So a couple of points I want to ask, and again, I don't want to derail your thought process a whole lot, but maybe if there's like I could take offline 2 points. One is the Elon Musk theory, right? Like from Shanghai to San Francisco, how does it go in 1 hour? So that could be something I wanted to see. Is it because of the third normal form he's talking about, or
he's not talking about that?
Or
what he's talking about is flight. So his point is slightly different. What he's saying is that, see, suppose you are here on Earth. Right? At this moment, it's a very counterintuitive argument. When you fly from here and you go along this path, you get a lot of, see, what is preventing you from going fast? There are two things in an aeroplane. One is that the air drag. So to overcome the air drag, you have to burn a lot of fuel, isn't it? But then you can go to higher altitude to reduce air drag. The trouble with going to higher altitudes beyond 33,000 feet in airplanes, for example, is that there is not enough air. So there is not enough air to even have a lift. You realize that, no? The airplane, what does it do? The airplane flies because the engines are, let's say that this is the engine. The jet is sucking in air and it is pushing it down. Yeah. If you look at the engine, you'll see a slight angle here. And the flaps, what they do is, because of the flaps and the shape of it, it basically what you have is action and reaction. This pushes so the air pushes the engine up or the whole aeroplane up. Yeah. That's how aeroplanes fly. So you need enough air to push back. If you go to too high altitude, the drag will be less, but there won't be enough air. So your airplane will literally stall and start falling. Right. So the point with that Elon Musk is making is that it is time to go beyond this low altitude flights. Right? This
is, so he's calling it like a rocket taxi, right?
Exactly. So what he's saying is,
rocket taxi.
From here, you just take a lift off. You lift off and you go straight into the ionosphere. Right? So you don't care about air at all. You literally go above the stratosphere into the ionosphere. Right? And in the ionosphere, you're not relying on the air to take you forward. You're instead relying on rocket fuel, the action reaction. You're burning fuel, right? A lot of fuel. How does a rocket go? It emits out a lot of hot gases, a lot of hot fuel, right? And the thrust is taking the rocket forward. So the idea is that if you go into this, the speeds that you can sustain, they are more in the order of 10, 20, 1,000 miles an hour. Right? So for example, a typical, for example, the space station, how long does it take to orbit the Earth?
15, 18 minutes.
Exactly. It's less than half an hour. So you have literally, you can see a sunrise or something like that. You literally orbit the Earth very, very fast, right? And some of these flying satellites, low orbit satellites, they also go half an hour later. So what it means is that if you go here, then most of the time this time is practically zero, because Earth is actually a very small planet. Once you are out, you are zooming very, very fast, right? Your bigger risk is not can you go fast, but will you just fly off the Earth altogether? And so the most of the energy goes, or time goes in going out of Mother Earth, escaping the gravity, and then later on, of course, falling back in. Right? Falling back in is a control thing. It's dangerous, but if it is controlled, it's not that time consuming. But the real time goes in accelerating out of Earth's gravity. And so you can actually go from here to Shanghai and any of these things in the limited amount of time, hour, half an hour, whatever it is that's being projected. And most of the time will not be the space travel time. It will be the time to launch.
Yeah.
And the time to gradually land, slowly land. So that's what they're talking about.
So still geodesic, right? If you look at geodesic, that's the smallest distance.
In some sense, you usually don't call it geodesic. You say that in view of the accelerations and things like that, it is still the best path that you can take. If you just lift out. So here's the thing. What you're doing is, if you think of Earth as flat, let's say San Francisco here and Shanghai here, what you're doing is you're going up, then you're taking the shortest path, and you're coming down.
Okay.
But normal geodesic would be like this, but you're not doing that because this is too much air drag. And you can't go fast because you're using air flight, and you can't have a rocket go through the air because the rocket will literally burn itself out. As you know, when rockets enter the airspace at very high speed, the cone is burning, actually burning. You need a very high temperature ceramic cone at the head of a rocket so that the rocket doesn't burn itself out. Actually, the return vehicle rather doesn't burn itself out. Yeah. That is actually the riskiest part of the space flight, the re-entry. It is absolutely burning hot. It's a fire. So you can't have a rocket that goes through air. You can only have a rocket that escapes the Earth, goes into the ionosphere, travels and comes back. And that's the whole point of this. The new approaches people are trying. They're saying that we are in the post-aeroplane era. Aeroplanes are way too slow, and we need to go beyond that. With aeroplane, there is a fundamental limit. You can't go beyond a certain height or altitude because there is not enough air, and you can't go beyond a certain speed with these jumbo jets. You guys probably know that, right? Once you come close to the sound barrier, there's massive sonic boom, and the aeroplane itself goes through huge stress. You can't take a normal aeroplane like a Boeing something and try to reach the sound barrier. The entire thing will just destruct itself. There'll be too much damage. So you need to make a very, very hardened planes, small planes that can cross the sound barrier. So which are not transport vehicles, which are just military vehicles. So space, air travel has reached a fundamental technology limit. We need to use space for travel. So anyway, that's a digression for the distance. Yeah, but see, what happens is that when you think about what distance is, it's a very fascinating subject. Einstein thought about it all his life. What does space-time mean? What does distance mean? And he came up with the theory of relativity, and that work is still continuing. My work in the doctoral work was also related very much to this. So obviously, if you ask me questions in this space, I can just go on talking for hours. So, but coming back to Earth. In K-means clustering, what we do is we just find a way to determine or identify whatever number of clusters you want to see. If you want to see 3 clusters, it can find 3 clusters. But then the question remains, what is the optimal number of clusters? And that's a hard question to answer. The best way you can do it is you have to look for the so-called elbow. You have to draw the scree plot. You have to look for the elbow in the scree plot. If you don't see clear elbows, as we saw in the lab in Saturday, it could be either because there are no clusters or because K-means is not the right algorithm to find the clusters. K-means has one big limitation. It looks for globular clusters, roundish clusters, convex-like clusters. If you don't have convex-like clusters, like as we did in the lab, and then this K-means doesn't, and the whole family of K-means doesn't quite work. Right? Fortunately, there's a last class of problems where it sort of suffices. So it's a very popular and easy clustering algorithm. It has spawned a whole sort of a subfield of clustering in itself. The enormous amount of variants of K-means clustering. I haven't talked about it because it's an introductory class, and we can go on about it. We can literally have a 10-week workshop on just clustering methods. So there is expectation maximization, and there are many, many variants of K-means. Expectation maximization would say, what if a point we don't absolutely assign it to one centroid? You say that 90% it is in this and 10% it is in that. Yeah. So when you start distributing the probabilities, the generalization of K-means becomes expectation maximization. And there are many, many things. Now, agglomerative clustering is different. Agglomerative clustering, if you remember, it breaks up the space into what? It takes all the points, calls all the points a cluster to begin with, and then it starts agglomerating it, joining the points together and making bigger and bigger clusters. And as you rise up, you have the choice that at the end of it, you have just one big cluster. So depending upon where you cut the dendrogram, this hierarchical representation, you can get as many clusters as you wish between one and the number of points. So in many fields, in medical domain especially, this is considered very, very useful because people often look at the problem at different levels of granularity. There's a lot of dynamics going on there in the body. So in the chemicals and chemical reactions, metabolic reactions and whatnot. So there's a lot of interesting things happening there. But today, so that's a review of last time. Today, I'm going to teach you a completely different kind of clustering called density-based, what did I just do? Density-based clustering. So what do we do in density-based clustering? Density-based clustering takes the same analogy, which is that if you have points in a cluster, think of all of these points. So actually, let me take bigger size points to illustrate this. Suppose you have a situation like this. And let us also take a few outliers, things that don't really belong to either of the clusters. So you notice that there's a very peculiar situation. You seem to have two clusters. What you would ideally like to do is say, I have this cluster and the rest of the points are outliers, right? Density-based clustering is very good at doing that. But the way it does it is it applies the notion that points have mass. And so wherever the points are, wherever you have clusters, you have a much higher density in those regions, in cluster regions. That makes sense, isn't it? For example, if you take a unit space, there will be far more points in the unit space in a cluster than outside it, than let's say here or here. Does that intuition make sense, guys?
Yes, sir. Yes.
It's a very basic common intuition. And so we use that intuition. And this work was quite interesting. It came towards the end of the last century. You would imagine in hindsight that this could have been discovered much before, but surprisingly, it actually came quite late. And it's based on some very interesting mathematical arguments. The first variant was DBSCAN. This paper was written by, I believe, three writers. And this paper was considered such a fundamental improvement upon clustering algorithms that it was immediately awarded the best paper of the year award in the field of machine learning, if I remember right. So what is this? It actually takes a little bit of an abstract perspective on clustering. So I'll take you through a slightly abstract mathematical journey, and you may for some time wonder, what am I doing? Why am I talking so abstractly? But just bear with me. It's not a long journey, just a small journey. So we will establish some basic concepts or notions. Concepts. One concept is the epsilon distance. The second thing is a direct neighbor. Direct neighbor, and the other is indirect neighbor. Then interior points. The other will be boundary points, and these things will become very intuitive in a moment. Boundary points and then outlier points. So these are all attributes of each data point. The epsilon distances, so let's start with the very basic. We say that use a cutoff of distance. Now, take a small distance. Cutoff, right? Or think of it like from a point you have a very small lamp and it can shed light only within a certain distance. Or another analogy would be that imagine that you have at each point, at any given point, you tie a string, and that string is only this long. So you can visit only this distance. You can only visit a circle of radius epsilon, isn't it? From point X. Visit this looks obvious, guys. No, you cannot go outside this. This is your region that you can visit from X. If all you're allowed to do is go epsilon distance. So far, so good, guys? So that creates the notion of the epsilon distance. Epsilon distance or epsilon neighborhood. Let me just call it epsilon distance or epsilon name. Region distance from the point X. So far, so good. Now you ask this question. Is another point, so let me call this point X0. Let me mark this point X0. Right? Now you ask this point, in this region, the epsilon neighborhood, does another point exist? Let us say that there is such a point. Let us say that this point exists, X1, which I'll put at this point. So this distance, you would agree that distance from X0 to X1 is less than epsilon, right? Would you agree?
Yes.
So if this is true, if and only if this is true, we say X0 and X1 are direct neighbors, directly reachable from one another. I.e., they are direct neighbors. But then imagine another point like X2. What about X2? What can you say about X2? Is X2 in the direct neighborhood of X0? What's the answer to this, guys?
No.
It is no. So the answer to that is no, it is not true. But X2 is in the epsilon neighborhood of x1, isn't it? So for example, let us see this. If I make an epsilon neighborhood, oh, actually it may not be true. Let me redraw x2 and make it a little bit closer to make my argument.
Yeah, otherwise it will be outlier or something.
It will become too far. So let me put that point here, x2. Yeah. So x2 is outside the direct neighborhood of x0, but it is, if I look at the epsilon, which is this much, I realize that the epsilon neighborhood of x1 is this. Are we together? Where this distance is epsilon. Right. So x2 belongs to, let me just mark it like this. x2 belongs to the epsilon neighborhood or direct neighborhood of x1. So we say that x2 is reachable from x1, from x0, and directly reachable from x1, right? So how can I go to x2? I can take this path. I can take an indirect path, what just happened. I can take a much more indirect path. I can go from x to x1 and from x1 to x2. Do you see that? It's a two-hop journey. Right? X to x1 and from x1 to x2. This is possible. Do you agree, guys? If you look at it, so they are reachable from each other, but they are not directly reachable. X0 and x2 are not directly reachable. So this is all we need. Now comes an interesting point. We consider or we define an epsilon neighborhood of a point to be dense. This is the word, dense, if we can find some neighborhoods n directly and neighbors in the direct and neighbors inside the neighborhood. What just happened? I have no idea. I'll rewrite it. So for example, if I have this point X and I draw the epsilon neighborhood and I have points, points X, let me call this X0, X1, X2, X3, X4, right? And let's say X5, X6. You can clearly see that this looks X7. Suppose I have N is equal to 5. I'll take some number, 5. So are there 5 points in this neighborhood? The number of points in the epsilon neighborhood of x0 are, how many points do we have? We have 7 points, isn't it? So if the number of points in the neighborhood of in the epsilon neighborhood of a point exceed n, and we can pick n, a sensible value of n, 3, 5, whatever, then we consider that region dense. Right? Now, does it agree with common intuition? Dense regions are, for example, dense housing. When you live in the suburbs, what is dense? You can practically share, books or stuff with your neighbor by stretching your hand out of your window and your neighbor catching it, isn't it? In the Bay Area, that would be considered dense living. On the other hand, if you're in the middle of, let's say, Idaho, or the heartland of US, any one of these states, Wyoming, then your neighbor, maybe you have to get into the car and drive half an hour to 1 hour to visit your neighbor, right? So those regions are not densely populated. They are very sparsely populated. Whereas if in a certain diameter, if in a certain radius, you can find a lot of neighbors, it is a dense region. Do you see how it agrees with common intuition, guys? Any feedback, guys? Are you understanding this? It's very
So how you define n?
Yeah, so those are the hyperparameters of the model. We need to pick sensible values of n and epsilon, right?
Okay.
That's the tricky part. Based on the domain, based on the situation, the hyperparameter of the model are hyperparameters. So you have to agree on a sensible epsilon and n. Right? And n, people often also call it the n points, ETS, number of points that you must have in the neighborhood. Right? This word is also used, but I'll just use n. Now, the thing is, so once you have chosen this, now what can you do? You do the following. The algorithm is this. Take an arbitrary point. Take an arbitrary point. Let's take the point xi. Then find its epsilon neighborhood. Answer is, did you find n in its n points in its neighborhood? If not, it may be an outlier. You don't know, right? If not, it is not an interior point. Then what you do, you can just sample around and try another data point till you find an interior point, a point whose epsilon neighborhood is dense. Are we together? Then find an interior point. Epsilon neighborhood. This is it. Sooner or later, you'll stumble across an interior point. Now, what you do is, from the interior point, reach out to every point that you can reach out, directly or indirectly. Find all points, find an interior point, find all points reachable, directly or indirectly. From interior point X, from X, right? So from X, right? Interior point X. Are we together? So what it means is, intuitively, let me show you what will happen. Suppose you have a cluster like this. Let's take an example, and this, some outlier points. Suppose you end up with an outlier point, you'll end up ignoring it, right? Sooner or later, let me color the points that you'll end up with. You will end up with this point, right? Let's say that your epsilon is this much. This is the size of your epsilon. So what will happen? Let me draw more points here. More points here. There's. Let me make it dense. So what will happen? Soon, suppose every point that is reachable from this point, you start coloring red. You'll end up coloring these guys red. Isn't it, guys? Huh? You'll end up coloring these red. Now from those points, again, more points are reachable. And gradually, all the points that are reachable will end up becoming like this. Are we together? Right. So find all the points reachable from X. So you can start with any arbitrary interior point and you'll end up with the same coloration, isn't it? And you won't end up reaching this cluster at all. Let me call this the cluster A and the cluster B. You realize that if you start with the point, any interior point in A, you will end up coloring all of A, but not B or not the outliers. Does this look obvious, guys?
Yes.
It is that. So what you do is you declare it to be a cluster. You declare it to be, we just found a cluster. Then what you do is you take another point, again try to find an interior point, sorry. Let me just pick another interior point.
Is it like you keep changing the centroid and measuring the distance from
You're not doing anything.
the chosen point to all of the points?
Yeah, so what we do is, let's take with this point, right? So suppose you take this interior point. What will you do? You will find the circle here. You will end up saying, okay, suppose 3 is my number of neighbors I need is 3. I end up coloring these as my neighbors. Then from each one of these, again, you draw another circle. You will end up picking up more points, right? And then from this, if you end up, this point will get colored because you're continuously drawing circles around each of the interior points. So you will end up coloring all the interior points. Does this make sense, guys? Haripriya, does it make sense?
Yeah, no, my only question is, so the circle is of the diameter epsilon, right?
Radius epsilon, yeah.
Radius epsilon. So which means that okay, the cluster just keeps expanding as much as possible, right?
Yeah, so in the beginning, you don't think cluster. What you do is you reach to every point reachable from an interior point, directly or indirectly. Right. So you will end up picking all the points and you declare those points to be your cluster.
Okay. Okay.
We found another cluster. So you keep on doing it. After a little while, you won't be able to find like these points removed or whatever points remain after that. You'll realize that they don't fulfill the requirements of being interior points. Because they don't fulfill the requirements of being interior points, you just declare them to be outliers. Right?
So Asif, so for this outlier, so if let's say there is another point close to it, so let's say there are only 2 points. So will it be considered a cluster or no?
No, I'm sorry. Repeat the question.
So if there are only 2 points, so let's say like between A and B, there is one, so 1 point, right? So let's put another point very close to that. And
A and B.
yeah, between A and B, there cluster A and cluster B, there is 1 point, right?
You mean this point? Okay. And so
the question is,
let's put another point very close to it. Yeah. So
will be considered as a cluster.
Is
right?
this considered a cluster?
no, it is not considered a cluster, but I'll tell you why. Let me first color it properly. I'm getting my colors wrong. Okay. So you're seeing these 2 points, right? Right. Now,
Yes.
let me just give them name, pi sigma. Pi sigma are not a cluster because this is not an interior point. What is the definition of an interior point? Suppose your n is equal to 5. Does it have 5 neighbors? It doesn't have 5 neighbors.
Oh, okay, got it. Yeah.
And so this will still be considered an outlier point. Right? Since
Suppose if there are 3 points here, let's say pi, rho, and sigma.
Right.
Now you declared n equals to 2, then this will become a cluster.
Then it will become a cluster. Yes, then it will become a cluster. So that is why it is very sensitive to the does not have n neighbors. 5. So that's the point. For something to be considered an integer point, and therefore the starting point of recognizing a cluster, you must fulfill the conditions of an integer point. You look at the epsilon neighborhood and you must find at least n neighbors. If you don't, do that. Now, the problem with this algorithm, DBSCAN was widely successful, but it has the main problem that it has is the hyperparameters. Like based on the hyperparameter epsilon and n, the clustering is very sensitive to it. Like for example, if a number of neighbors is 2, then these two outlier points that we talked about, a pi and rho, they'll become a cluster, isn't it? But for n is equal to 3 or more, a pi and rho are not a cluster, they're outliers. So, and what we realize is that the shape of the cluster also tends to be a little sensitive, quite a bit sensitive to epsilon and n. So that was the weakness of DBSCAN. It was that it's very sensitive to the hyperparameters. But while that weakness is there, it's sort of very effective. It works with non-globular clusters and so forth, like we saw in the lab last time. Right? Saturday, we did the lab and we saw it. It works just fine with non-globular clusters. So that is DBSCAN, guys. Huh? Now, trouble with DBSCAN is it doesn't scale to big data. When you have massive number of points and you have to run a vast cluster, it's a little slow to scale. So people were searching for a more scalable algorithm, and they came up with another algorithm, which is also density-based clustering, but these days it was thought very well of, DENCLUE. So DENCLUE is already into DENCLUE 2.0 and this and that, and Google has an implementation, very high-speed implementation and so forth. This is one of the very beautiful density-based clustering algorithms. I'm going to talk about it. Let's take a 5 minutes break and get back. Huh? Drink some water. Let's have a 5 minutes break and we'll come back here. In the meanwhile, let me pause the recording for a moment.
So for DBSCAN, when it scans a point, the algorithm just rewards a point. It doesn't penalize a point for not being part of a cluster yet, right?
No, it doesn't. So all it start with the integer. Essentially fan out and keep pulling in more and more points.
Right, because if it picks a boundary of a cluster as an integer point, it might not have enough in its neighborhood, but it might be reached by another point, right? That's why it's still.
Good point you made. What you just said. If you look at this point, this point does not have enough neighbors, right? But it is reachable from one integer point. You see that you can reach from this to this, isn't it? And so these points, they are called boundary points. And so when you discover a cluster, you will with integer points and boundary points. You start from an integer point and ultimately you'll stop at the boundary points. Are we together?
Yes, sir. So if it picks a boundary point as an arbitrary point first, it will not penalize it, right? It will just skip it for now.
Right away and say, oh,
so it can just reference the point back when it realizes it's a boundary point. Okay, that's why it takes time. Okay.
See, what happens is if you just happen to pick either a boundary or a exterior point, right, the outlier point, it won't have enough neighbors. So you know that, oh shucks, you started with a wrong guess. Let you go about hunting for an interior point. Now that interior point might ultimately find out and reach this boundary point. And so then that interior point will end up owning the boundary point in its own cluster. So did you get that, Patrick? It's a very simple approach. Keep fanning out.
Yes,
You
sir.
can grab as you can, but you cannot make a jump of then epsilon.
Sir, my only question there is, what if that boundary point is close also to another cluster? So if you pick another one, yeah.
Let me answer your question. Let us take this sort of a situation to illustrate your point. Suppose you have a situation that you have boundary points like, you have points like this. And then you have this point, and then this point, and then this point. These points are here. Now the question is, and this is where the DBSCAN becomes very sensitive to what your epsilon neighborhood is. Suppose you start coloring points. Suppose we start going about coloring our points. Where is the red point gone? Yeah. So suppose you start here. You'll end up coloring all of these points. Right? Then the question comes, you reach this point. You have reached this point from an interior point, isn't it? You went like this, you reached here. So it is still part of the red cluster. The question is, what is the size of the epsilon neighborhood? Suppose your epsilon neighborhood is this big. Then what will happen? It will end up grabbing this point, isn't it? Even though it was a boundary point, it could reach this point. Because it could reach this point, it will start fanning out here. And so it will end up discovering that there is actually only one cluster. Isn't it? Because everything is in the epsilon neighborhood of, let's say that this was your initial point, everything is reachable from that initial point. Do you see that, Patrick? Right. So you would say that you just have one cluster if your epsilon neighborhood is this big. On the other hand, if your epsilon neighborhood is this big, only this big, then, or just this big, then what will happen? This bridge cannot be crossed. From here to here is epsilon. You can't cross over to the other side, to the right-hand side, isn't it? And so what you will end up with, in this case, is this as one cluster and this as another cluster.
Yes, sir, I understand. What I think, sir, is the point that crossed over. What if that's a boundary point for either of the clusters? It can get selected to either the left cluster or the right cluster based on which points were.
No, Patrick, it's a sequential part. If you start here and you fan out, the only question is this point within epsilon? Let me name these points, alpha, beta. Right? Is beta within epsilon neighborhood of alpha or not? Alpha is certainly a boundary point. It doesn't have enough neighbors. But is alpha and beta reachable from each other directly? If they are reachable from each other, you started from this nucleation point, you'll end up grabbing all the points. Once you have grabbed a point, it doesn't remain for another cluster to also claim it as its point. You realize, right? It is out of scope now for the next cluster.
I understand, sir. But if beta, it looks like a bow tie. So if beta is the middle point, and there's not enough to fan out to another side. So, but it's enough to
think about it this way. Let me draw it out for you. There's a central point. We're trying to make bow tie. Let's say that we put beta here. Let's say that there's alpha and there's alpha.
Yes, sir.
You're an echo.
Yeah, Patrick, you'll have to mute yourself for the time being. Yeah. So the only thing that matters is whether from alpha. So suppose you start from this direction. From alpha, can you reach beta or not? You can pick an answer. Either you can or cannot. If you cannot, then beta stays sitting there. Likewise, suppose you start from here and you reach gamma. Either you can reach beta or you can't reach beta. Let us say that both from alpha and from gamma you can reach. Let us say that this was your starting point. From alpha you can reach to beta, from beta you can reach to gamma, and from gamma you can reach to everything else. Right? You can reach out to everything else. So therefore you have just one cluster. Patrick, are you getting the point?
Yes, sir. I understand. I understand from alpha you can get to beta, but beta going to gamma also. If they're assuming alpha to beta and beta to gamma are all equidistant, that means you can pull the whole cluster. It pulls the whole cluster.
Yeah, of course. See, you keep fanning out. Every point that is reachable from a point that has already become reachable, right, is now part of your cluster. So let's make it very real. These days we talk about a COVID thing, right? So there is one person, he infects 5 people, who infects 5 more people within 6 feet of him. It doesn't matter. That infection will keep on spreading until there is nobody within 5 or 6 feet remaining, isn't it? So suppose 50 people have gotten infected. When will the growth of that infection stop? When nobody comes within 6 feet of those 50 people, isn't it? That's when that cluster will stop forming.
Okay, sir.
On the other hand, if alpha, beta, and gamma are less than 6 feet apart, then both of these, the entire bow tie will get infected as one cluster.
Okay, sir, I understand. So as long as a point gets converted into that cluster, it can serve as another point to reach. Okay, okay. And then if it reaches a point that can scan again within the epsilon, it will convert an entire cluster. It will convert the entire neighborhood as the same cluster.
Yeah, and actually, infectious disease is very intuitive. A thing that you start with one initial point, which is an interior point. Think of him as the case 0, the patient 0, and he starts infecting. So the person will keep on infecting till there is nobody to infect. Why? Because all other people are too far away. Right? So all the people that the person infected directly or indirectly, right? That whole infection is one cluster. And in fact, that's how you think about it in epidemiology, as one cluster. So that's that. Do we get it? So as you can see, this is very sensitive to the choice of epsilon, the size of your neighborhood, and the number of points you expect in the neighborhood, which has been a weakness, sort of sensitive to that. It's not quite a weakness. But
Asif, another question. So between like DBSCAN and K-mean, what will be a situation when we should be using K-mean over DBSCAN?
see, generally, right, K-means is cheaper in lower dimensional spaces. Right? In very high, see, here's the thing. A K-means is relatively cheap because you just have to find distances to points and find the centroid, right? But for each point, you just have to find the distance to the centroids. But in a DBSCAN, for each point, you have to draw the epsilon neighborhood and see what other points are in the epsilon neighborhood, isn't it? So computationally, DBSCAN is more expensive. However, DBSCAN in general gives better clusters, in my opinion. Broadly, it tends to give better clusters. But the trouble with DBSCAN is it's very sensitive to epsilon and n. So now I'm going to tell you another algorithm, which is actually superior in the sense that it is massively scalable, very, very fast, and is not so sensitive to the hyperparameters. So that thing is called DENCLUE. If you guys can, if you have to, they tend to if your computing resources can sustain it, preferably go with density-based scanners. They're superior. They give you better clusters. They're less unstable if your clusters are non-globular. Right? So to establish DENCLUE, we need another mathematical concept, a concept of influence function. Influence function, right? What is an influence function? Think of it as like this. Suppose you have a source of light. Imagine a little lamp. Now the lamp will shed light only up to a certain distance, isn't it? After that, as you go away, further and further away from the lamp, the light from the lamp will keep decaying, isn't it? So if you were to look at the intensity of light based on distance from the center, distance from lamp, from flame of the lamp, would you agree that the distance would go something like, it will decay. It could go like this, it could go like this, it could go whatever it is, but it will decrease with distance. The light intensity, right? The light intensity. And it's a very general, by the way, light intensity, we know exactly how it goes. It goes 1 over r squared, but imagine some other sort of influence. But one thing we are sure that further you go from the lamp, the less the influence. Does that intuition make sense, guys? Right. Or another way to put it is, you can think of this point as a heavy point, and it is pulling other points towards itself and so forth. I don't like that analogy, but okay. Let's just use the light analogy, light intensity. So these functions, the distance between x and y, let's say that x is the source and y is some arbitrary point, is some decay function. These are usually called the influence functions. Now comes an interesting thought. Suppose I have 3 points, 1, 2, 3, x1, x2, x3, right? 3 points. And I'm looking at the total influence at a given point x, right? Let us on the point x from x1, x2. How will you do that? You would definitely say that it is equal to fx, whatever function it is, x, x1 plus x, x2 plus f, x, x3. Would you agree? This is the x point. It is the, or the light intensity at this point x. Let me color it something else. At this point will be the sum of the influence from the 3 points, right? Do you agree with that, guys? The total light intensity. So suppose you are sitting here and trying to read a book. You would agree that the light intensity will come, or the luminosity will come from 3 sources, and all 3 lamps will contribute a little bit to the brightness of light, which is helping you read a book at X. Does that make sense, guys?
Yes, sir.
And so you can say that the influence, and so I'll write this equation, the total influence at a point, arbitrary point, at an arbitrary point, let me just say, arbitrary point X in the feature space Rn is summation of fx and all points xi that are available. Right? let me just call this the total influence function. The total influence at x. Would you agree, guys? Actually, let me use a symbol that people tend to use, or rather I tend to use. I'll just use a phi, a total influence at this point, just to distinguish it from the f. F is the influence from each of the points. Would you agree, guys? So far, so good. Now the question is, what do you choose as fx? One common choice that people love, and it doesn't really matter which influence function you take, so long as it decays with distance. Or the word that people use is it's a kernel. When you go to ML200, you'll see me use the word kernel. Right? So long as it is a kernel, it is fine. So one common decay kernel influence function that people use is this, the Gaussian function, the bell curve kind of a function. They will take the function xi, the distance, is equal to e to the minus d, the distance between x and xi, distance square over 2 sigma square. Now, sigma is sort of the measure of the neighborhood that you are willing to consider. It doesn't matter. So just think of it as a sort of a hyperparameter, or actually it doesn't make that much difference, but okay, we'll keep it there for the time being. Now, what is the nature of this function? It decays with distance. Are we together? So far off points don't contribute much influence. Nearby points compute a lot of influence. So does this look familiar, guys? We have done the bell curve so many times that this should look very familiar now. The normal function, the Gaussian function. Let me just write.
Yes. Yes.
Up to a normalization. I'm forgetting the normalization coefficient, right? I forget the normalization. Let's not mention it. So it's a number that will go from 1 to 0. Now comes an argument that makes it very powerful. See, what happens is that you can suppose there are two sets of points. Let me make two clusters. And another cluster. Let me just take it like, oh, sorry. This is terrible. 1 second. I'm trying to make it green in color. Why is this not becoming green? Green in color. So you have this. Now think of a point here. I'll take a red point here or white point here. Suppose you have a point here. This point is your x. Now you realize that it is coming under the influence of both the clusters, isn't it? But if you look at you ask an important question: in which direction from x should we go for maximum increase of influence of phi x? The phi x, sorry, used to x, phi x. So in other words, I can go here, I can go here. As I go here, these points will have different amount of influences on them. But the question is, in which direction should I go to have a maximum increase of phi? So that direction, you would agree, would be a direction like this, isn't it, guys? Somewhat like this, isn't it? This would be the direction. Let me make it like this, somewhat like this. Would you agree? Because at the top here, this is the most illuminated point, and this is the most illuminated point of the green cluster. The nearest cluster here will exert far more influence than a distant cluster on the point X, right? So if I come closer to the blue cluster, very rapidly, the light will increase as I come closer and closer to the blue cluster. Whereas if I move closer and closer to the green cluster, the light will increase more slowly because the green cluster is far away. Does that make sense, guys?
Yes, sir.
Yeah. So that is the intuition. That's a very important intuition. And you can say that more mathematically. You can say that you can take a path of call grade, like a hill climbing algorithm. Hill climbing. What you do is you follow the next point. The next point, let's say that x prime is equal to the previous value of x, plus take a small step and take the gradient of phi x. Now, does this look very familiar, guys, this equation? It is the opposite of gradient descent. If I replace the plus with a minus, what does it become? It becomes the equation of gradient descent, isn't it? This is the gradient. This is the gradient of the influence function. So in other words, you take a small step in the direction in which the gradient is the highest, you know, the maximum increase in the influence function. Does this journey make sense, guys? Anyone, guys? I hope this by now should look very
Yes, sir. It's clear.
straightforward.
Yes, it's fine.
And so what will happen is you will end up very quickly rising to a point, and I'll mark it as a red color, or let's give it some color that I have not used. No, yellow on white doesn't look good. Okay, let me use this color. You will end up with this point here. This journey will very rapidly take you to this point. And then suppose you start from another arbitrary point, let's say here, very quickly the journey will take you into this, right? To this point. These points are called, these are called attractors. These are the points of attraction. That is where the light intensity or the influence functions achieve their maxima at attractors, at the attractor points. Would you agree? They achieve local maxima. In other words, the following condition will be true. And those of you, this is a bit of calculus. If you know it, it's good. If you don't worry. The gradient will vanish at maxima and minima. The gradient vanishes. In other words, it's flat on the top of the hill or the bottom of the valley. You remember, there's no slope there. Right? And there is a second condition, which is the Hessian, which I'll just mention, but you don't need to remember that, the Hessian. Hessian is negative. Right? Hessian is defined. In fact, if you're interested, I will just tell you what Hessian is. It is d phi dx 1 square. Suppose you do x1, x2, right? In 2 dimensions, if you do the Hessian of a function phi, which is made up of just 2 dimensions, let us say, right? 2-dimensional space, then it would be phi square dx1 dx2 d square phi dx1 x2, and this is a bit of calculus. If you don't remember, don't at all matter, and frankly it's of no practical use at this particular moment, but it is just worth knowing that there is such a thing as a Hessian because the literature keeps talking about it. It is a generalization of the second derivative. If you go back and look at your old high school textbooks, you'll realize that at maxima, the Hessian tends to be, the second derivative tends to be negative. Right? And so the same thing applies here. Maxima of these will be. So forget the mathematics. All you're doing is you're finding intuitively the points of highest luminosity. When you find the points of highest luminosity, then what do? You set a cutoff of how much influence you have, what is the influence at a given point, and you put a certain level of cutoff on the influence, that if the influence is below a certain threshold or the light at a given place is below a threshold, you'll consider it to be a dark spot. And all the illuminated points are clusters, right? Whereas points like this are not in the cluster because they are not sufficiently illuminated. Does that make sense, guys? You see the reasoning here, very simple reasoning. You keep following the light and if you try to find the nearest, brightest light spot, in a sense. When you reach that, you have found an attractor, right? Or the hilltop. The most illuminated point, and then that zone of illumination is a cluster. Now, why is this algorithm very scalable or fast? For one thing, you can see what you can do is you can start with a sample of points, and with a sample of points, you can find the attractors. Once you have found the attractors, all you have to do is for every point, you can just assign it to the nearest attractor. The computation can go very fast from that. In fact, you don't even have to assign the attractors. Once you have found the attractors, forget about the points. You can just say that you have found the clusters. And if somebody asks you which points belong to the cluster, then you can lazily go and compute it that, okay, these are all the points that belong to my cluster, and those are all the points that belong to that cluster, and so forth, right? So it's a very fast algorithm, scales very well, which is why it's well considered actually in big data circles, in scalable circles. One reason, for example, the likes of Google, etc., keep having a high-speed implementation of this. So this is all there is to clustering. Right? We did 3 methods of clustering: k-means clustering, hierarchical clustering, and density-based clustering. So DENCLUE, it's a little bit hard to find Python implementations. But you do find C implementation, C++ implementations are there. You can use it. What happens is a lot of these DENCLUE algorithms are made into executable libraries. You can just fire it onto the data set and run it and so forth sometimes. So you can use it, or maybe, I don't know, I have not checked the latest situation, whether DENCLUE is available in Python or not. Maybe if you guys find a DENCLUE implementation, let me know. Oh yeah, somebody has implemented DENCLUE in Python now, comparing clustering algorithms. Okay, DENCLUE to GitHub, Python. DENCLUE algorithm for Python. So yeah, some people have done it. They have done it in pure Python. Generally, when you do it in pure Python, as you can imagine, Python is a slow language. So it doesn't scale very well to do computations. But typically, when you use scikit-learn or you use a PyTorch or TensorFlow, Python is just a thin layer over underlying C++ implementations. Then it runs super fast. So if you guys find an implementation that under the covers is a high-speed C++ implementation, but has a Python binding to it, let me know. I haven't found it. I use it straight from C++. So, well, that is it, guys. That is the topic of density-based clustering. Now, I was hoping that we would finish clustering a little bit earlier. Then I could have talked about dimensionality reduction. But let me keep dimensionality reduction for the next time. And let me take now only questions in clustering. If you guys have any questions in clustering, you can ask me.
Sir, when does DENCLUE break off an area into more than one cluster if they're close to each other?
See, once again, there's a sigma. You have to choose what is the minimum density or the minimum influence at which you want to do the cutoff, right? So that is controlled by that sigma and so forth. So it is again a choice, and based on how much or where do you cut off, it makes all the difference. It is up to you. So let me elaborate this. See, for example, why is this? Suppose I have a white point here. Is this also part of I'll put a question here. Is this point a part of the cluster or not? It depends upon where you put off the cutoff on the influence, total influence. If you say my total influence should be at least, let us say 0.1. I'm just taking a number, 0.01. Then this point may or may not fall into your cluster. It may be declared an outlier or it may fall into your cluster. Are we getting it?
Yes, sir.
That's it. But the good thing with DENCLUE is, see, it's a field theoretic argument. People who come from field theory, people like me, we get very excited when we see functions like this, right? A function that operates, this influence function that operates on the space, the entire feature space, and this function is continuous, differentiable, and you can do calculus on it. We get very excited because what it means is that we are not doing discrete mathematics now, we're doing continuous mathematics. And in general, you can do it lightning fast. You can find your answers lightning fast, even when you have a large scale data. And that goes a little bit onto the technical side. Read up the papers on DENCLUE, DENCLUE 2.0. See if you can understand it. Usually, DENCLUE, most people find it a bit scary without some background. But now that you have a background, you can. Actually, why don't we do that right now? Let's search for a paper on DENCLUE. I'll do it together with you, and let us see if we can make head and tail out of it together. I'll just arbitrarily pick a paper on DENCLUE. Huh? Let me share something, share the main screen. So suppose I look at this. Are you guys seeing my screen? Are you seeing the whole screen or only a limited part of the screen?
The
Only
quarter.
seeing a quarter,
Oh, good.
top
The
right,
quarter
top
problem
left
is
quarter.
okay, let me solve that quarter screen problem. Or maybe the other way I could solve it is not sharing the entire screen, but by sharing only the browser. Share web browser. Okay, which one is it being shared? All right.
Still a quarter.
Still a quarter. Huh? Okay, then let me share. This is a severe limitation of WebEx. Give me a second. I'll have to decrease the resolution. Srini, is this a problem that you guys are aware of? That for 4K monitors, it becomes a bit problematic. 4K resolution. All right, we'll search for DENCLUE. Oh, there we go. DENCLUE.
As if we can't see your screen.
Oh, you can't see my screen. Okay, hang on. There is no screen. How about now? Can you see my screen now?
Yes.
Yes.
So if I look at DENCLUE and just say tutorial. So it's always good. By the way, one good website is not to go to Google, but go to scholar.google.com. Usually what happens is I have a special icon. Did you see this icon here? In my Chrome, I keep a special icon just for Google Scholar because it's a very quick way to find high quality papers on any given topic. So we'll do that now. Introduction to DENCLUE. Let's see what comes up. DENCLUE, citation, PDF. The first one. So here is a paper on DENCLUE. DENCLUE algorithm employs a cluster. So let's just scan through it and see if it is beginning to make sense. There's a Gaussian kernel, which of course we understand. And this is it. See, look at this. It is looking at the influence functions and trying to find the maxima of the influence functions. Now, does this make sense, guys? This update rule makes sense? It is nothing but the gradient, which they have normalized it by dividing it with, they have normalized the gradient by some quantity, but it is very similar to our update rule, isn't it? It's just an adaptation of the update rule. Then the total influence at a given point is again this, and you take a journey to that. I mean, this language here is much more complicated, little bit more complicated than the way I explained it to you. But this is it. Do you see this, guys? All you're doing is find these attractors, these points where the light is shining the brightest. And that is it. This will go into a lot more. Actually, the notation of this is a little bit more complicated than I would have liked. Maybe I should write a little article explaining it in simpler terms. Then to clustering algorithm. A new clustering based on KNN optics. Okay. A DENCLUE IM, a new app. Yeah. So usually these things should be good. Comparative study of various clustering algorithms in this thing, because well, it explains DENCLUE, it will hopefully do it in a simpler way. Yeah, density, and all you do is, I don't know what dot and dot mean. They all seem to use their peculiar notations, which is what makes these things actually, most of these ideas are very simple ideas, but they tend to get very complicated when written out as papers. Okay, this one we already looked. Let's look at this guy. This is not in PDF. Now it will ask me to log in with IEEE. DENCLUE tutorial. Let's try that. Download limit exceeded. The server is down. Okay, clustering techniques for large datasets. Okay, about the tutors client. Let's see how good tutors they are. Clustering techniques for large datasets. Application to marketing. So hopefully they'll come to k-means. We know this linkages are, yeah. Kernel density estimations. This is the thing we are coming to. Yeah. So do you guys see, by the way, the minus is not visible here where the mouse is, but you see that this is exactly what I explained to you guys, the density function, the influence function. Do you see this, guys? The total influence, right?
Yes.
That is it. That's a very basic idea. And what it means is that this influence function has peaks. Those peaks are called attractors, which this one doesn't seem to have mentioned. That is it. Actually, it's surprising how little good literature for explaining to people is available from some of these algorithms which are used massively. So maybe I'll write some notes. I'll add a chapter on DENCLUE to our notes, explaining it. And of course, do refer to this video. Was this explanation clear, guys, the way I explained it to you on the writing board?
Yes.
Yeah, it's a very basic
Fine.
explanation. That's all it is. If you think in terms of light shining, it will make it very obvious to you. Think of the total light shining at a given point from all the points. If you treat each of the sample points as a little lamp casting a light, or you can think of it as stars. So you ask at any given point, what is the total starlight and which point is maximally lit? Those are your attractors. That's all. The intuition is very simple. Unfortunately, when you write it in formal language, then a lot of notations creep in and makes it a little hard to understand. But that's all there is to it. There's nothing else. So guys, that's all I have on clustering. Now, this weekend, Saturday, I would like to introduce a topic called dimensionality reduction. And I would have liked to do the theory today, but I think we have gone on. Are you guys game for another hour and a half? Or should we keep it for next time?
We can do it today.
Are you guys
Yeah.
up to it?
That's okay.
Anybody?
Yes, sir. Let's go.
Okay. All right. Then let's again take a 5 minutes break and then we'll start on another topic. And if it begins to get information overload, let me know then. I'll pause the recording for a moment and we'll meet again in let's meet again in 10 minutes and then we'll have a long session.